This is my report which investigates Newton's second law of motion and in particular a non-zero value for Fnet. We will be using this form of the equation to enable us to predict motion future. We will be observing the motion due to gravity of a cotton ball as it falls from rest. We will be comparing the motion to the motion predicted by computer models. Firstly modelling for the weight force due to gravity alone, then taking drag due to air into consideration. For the investigation, the following was used. In the observation experiment, a video recording was made of a cotton ball falling in a near straight line path perpendicular to the camera view. A graph here and table here shows data points taken of distance versus time. Here is the data we'll need for the prediction model. The first model will be set to account for gravity as the only force acting on the mass. So here we've set the mass to 0.415 grams and the initial position and velocity to 0 as stated earlier and the time to 0. Here we've set a small delta t value for good resolution and a value of 9.8 for the value g, the magnitude of the gravitational field, and j hat has been set to 1 for the y-axis. The calculation loop has been set to 0.48 seconds, the duration of the video analysis. Here the weight force is calculated showing as mass times g times the direction. The sign is negative as the direction is in minus y. And Fnet is shown here as due to the weight force only. Here's Newton's equation in code format. And here where the ball's position is updated. And here the updated time. Arrows will be added to the visualization to represent forces. They will be proportionally scaled using this factor. Now we run the code and the data points are calculated. And here we see a graph and a visualization of the cotton ball falling. Note the arrow representing the weight force. And now we generate a new computer model to introduce drag into the equation. For drag we introduce a new proportionality constant which has been set to this value by trial and error, by making the last data point of the drag curve fit the last data point of the observed data. The drag force Fd is set here. As the drag force is in the opposite direction of the velocity, the proportionality constant b is set negative. This is the term for the squaring of the velocity. As ball.vel is a vector, we cannot just square it. So using mag magnitude for this part, it is calculated as a scalar, which we can do if we have only one component, which we do, and can then be used to multiply by each component in the vector, giving us the y squared component we need. And Fnet is shown here as the sum of the weight force and the drag force. Now if we run the program, we can see the graph and visualization. Note now the additional arrow representing the drag force and how it starts small and increases in size. Yet another computer model was then set up to model the effect of throwing the cotton ball with an initial velocity of 5 meters per second instead of from rest. And here is the only modification required for this program. Now running the program, note how the initial drag force arrow starts large, then shrinks. We now put all the data together on a spreadsheet for comparison. Up to the first 6 points of the observed data, we have a reasonably good fit to both models from rest, but then we see the model including drag slow the ball down as expected. After approximately 0.3 seconds, the curve of the observed shows a sudden change in the incline. This point was checked on the video and can be put down to the orientation of the cotton ball changing and having less drag. A point on the graph is shown where the terminal velocity has been reached, followed by points in a straight line showing constant velocity. A dotted straight line has been shown over the curve for the cotton ball which has been modelled as being thrown. For greater clarity, further models were run extending the total time to 2 seconds in order to better see the terminal velocity points being reached. Again, straight lines are included for reference. Note how both are straight lines and are parallel, showing same constant velocity. However, the calculation for the constant velocity differs to that of the observed constant velocity. The observed constant velocity is slower. This may be due to the drag coefficient b being set to the last observed point of the curve. But the curve comprises data points going through changing velocity and constant velocity. Perhaps this is not the correct way to set the value of b for this situation. Thank you very much.